All right, guys, this video is going to cover the basics of lesson 3.3 simply because the morning session is going to be eaten up by me being in a testing block and having to proctor. So please listen, please take some notes, mark up your paperwork, and here we go. 3.3 is pretty quick. So we're talking about transforming our data so that we can achieve linearity. And what that basically means, if you look at the picture right here, the data set in this area is not exactly linear right now. It is kind of curved. And regardless of what the data set is talking about, I'm just going to read what is written right here. Sometimes the scale of a data set is too large for a pattern to be recognized. And in this situation, you can notice that x-axis, you have some very large numbers that have to do with population. And when you have massive data sets that are going to take up a lot of space, sometimes it is too large for the pattern to be recognized. And when you're in that situation, if occasionally you're going to do a little bit of transforming by perhaps taking the logarithm or the square root of your data set, you might wind up getting something that looks a little more linear, like in the second image below. Now, something to keep in mind, if those words logarithm and square root kind of throw you off, you are not physically going to be applying the logarithmic function or the square root function to the data set. It will be output that is already given to you. So if you just glance down here at the second block of text, you're going to use transformations that involve raising your data set to powers, taking roots, and taking logarithms, which will sometimes, depending on which function you use, create a linear model that describes the relationship between your two quantitative variables. And then you are now allowed to make predictions. So once again, the data set we're looking at here is a very, very massive data set. So sometimes when the data sets are so large, you don't exactly see that linear pattern that we are trying to look for. But when you transform the data set with one of the functions that are listed there, logarithmic or square root, the data set can come out looking more linear. And then you are able to take any predictions you need to make and draw conclusions and all of that. So the example you're seeing here was the logarithm being applied to the data set, and now things are more linear. So let's take a look at just a couple other visual examples. And once again, you are not physically doing these functions to the data set. It is already done for you. You might have a data set that involves an exponent. So you would be in the situation right here, all of your x values are going to be raised to the power of p. P is just some arbitrary number that allows the data set to come out more linear than it would otherwise. Likewise, in the purple example here, you could take the square root of your y values, and that would allow a more linear pattern to be produced. Now, these two examples that you're seeing here are ones that are already worked out. So you would have been told, for example, that in this second function, the square root was already applied, and then you would see all the data stuff that would be written below, and then you would draw all of your conclusions involving standard deviation and so on and so forth, r squared and all of those values. What you are also allowed to do is, if you so please, you can apply the function to both the x and the y variable. So in this case, you are seeing that the logarithm is applied to both sides of your data sets, the x-axis and the y-axis, and just what's being talked about right here, and that can allow you to draw those exact same conclusions. You're going to notice some Algebra 2 math is written right here involving things like the power rule and the the change of base rule. I forget all of those specific names of those Algebra 2 concepts, but if you took Algebra 2 recently enough, then you would be able to tell that because the a and the x are being multiplied together, you are allowed to separate those with addition. But again, you're not going to be physically doing these actions. They are already going to be done for you. You just have to understand that because the data set right over here was so large, it became more linear when the logarithmic function was applied in this example. And in other examples, you'll see different functions will be applied to make the data set look accordingly. So just right down here at the bottom, you can see that little notice that sometimes Algebra 2 skills are required, but you're going to see the data set already produced for you. Now, I know that does sound very brief, and there will not be any examples shown in this video simply because I did not have enough time to build that for you. So let me just show you the summary instead of what is basically going on with 3.3. You want your scatter plots to appear linear. And if they're not linear, then when you apply a transformation to either x or y, or perhaps both of those values, you can produce a linear model. And when I return to class tomorrow, for those of us in the morning session, we will be clarifying more of this. Now, the last thing I will say is a very important summary of what I feel you need to be aware of regarding Chapter 3 before we enter the review phase. So if you are only partially listening until right now, please tune in extra carefully because I'm going to relate these 6 bullet points to the images that you see right here. So listen up. First of all, very obvious thing, a scatter plot is strong if the data is close to the regression line. So looking at the 2 little sketches I drew here, let's call this sketch number 1 and this will be sketch number 2. The first question would be, which one of those sketches is going to be stronger? And hopefully you would immediately say sketch number 1 because the data set is much tighter and closer to the regression line. Second bullet point, if the residual plot of a scatter plot is random, then the model is good. So I didn't pre-draw one of these, but let's just say you saw a residual plot with all of the data kind of scattered around. This that I just drew would be very good, a very good representation of the scatter plot. But if you saw patterns in your residuals, so maybe it was going up and then down and things look a little curved, then this would indicate a bad data set. And again, that is a residual plot, not the actual scatter plot, but the residuals. Once more, if your residual plot seems to have a lot of randomness to it, but there is a cluster, then your response might be it is a moderately strong data set, or perhaps it is moderately weak. Just a cluster or a pattern in your residuals are things that will make the overall model not a good representation of the data set. All right, moving on. Standard deviation. It is a measure of how far away the data points are from the regression line. Those words have been thrown around a lot, standard deviation, and I feel like we're not fully grasping the overall concept. So what I'm trying to say is the higher the standard deviation is, the more spread out the data is from the regression line. Look at these 2 examples. Which one of them is going to have the higher standard deviation? And hopefully you arrived at number 2 because all of the data points are a lot farther from the regression line than in example number 1. So number 2 is going to have a standard deviation that is higher than the standard deviation of the first image, which is going to be a smaller standard deviation since all of the data points are really close to the line. Next up, we have R squared. It measures what percent of the variability, and I'm choosing to use the word chaos instead of the word variability because, again, I noticed yesterday when we were practicing, some people were having issues really grasping what R squared means and just memorizing the sentence builder rather than understanding the greater meaning of it. And if you don't want to think of the word variability, then you can think of chaos. The chaos in the data set is explained by the regression model, and that is what R squared represents. The higher the percentage is for R squared, the better the model. And the higher R squared is, the closer the data set is going to be to the line. So for example, in 1 and 2, right over here, if the question were to be which one of these data sets will have a higher R squared value, value, you would hopefully understand that data set number 1 is going to have an R squared value that is bigger than data set number 2. And again, the less spread out the data is, the closer the data is to the actual regression line, then the higher the R squared percentage is going to be. Because again, the R squared value measures what percent the model does in representing the variability, the chaos, because not every data point is going to fall on the line. There are going to be data points above and below the line. So the measurement of how strong your data set is can be determined by R squared. The higher R squared is, the closer to the data set or the closer to the line your points are going to be. And then in the next bullet point, standard deviation and R squared are inversely related. Inverse meaning they are opposite. As one goes up, the other goes down. And if you look at the arrows that I just drew right here, you can see that inverse relationship. Starting up here at the top with the purple standard deviation, graph number 1 would have a smaller standard deviation because all of the data points are very close to the line, and therefore the R squared value is going to be higher because the variability is really small. The chaos of the data set is very nicely represented with your regression line because all the points are really close. The standard deviation was low. And then the opposite, vice versa, is going to be true in the second model where the standard deviation is much higher because all of the data points are farther away from the regression line. So because the standard deviation is higher in the second model down here, the R squared percentage of how much of the variability the line is accounting for, how much of the chaos is being measured by the model, that value for R squared is going to be a lot lower because, again, the data set is way more spread out. So, as it says in the statement, as the data spreads out further and has a higher standard deviation, the value of R squared becomes lower because now there is more chaos around the line. So higher standard deviation would be number 2 down here, and you can see that there is more chaos with all of those data points around the line. Lastly, I can see I did not draw one of these examples, so I'm just going to quickly do that. Let me just create this line right here, and let's go dots over here, and then let's throw one dot way over there. So what you are looking at in this example is what is called a high leverage point, a point with a massive X value that makes it linger very far away from the primary area of the data set. When you remove a high leverage point, it's going to affect the standard deviation and R squared values. Now, there are many examples of this. The example I'm showing you right here is a positive regression model. So just to talk about that point, let me just erase some of this highlighter really quick. There we go. Oh, one more little scratch mark right there. Come on. And there we go. Okay. Now, let's say this data point right here was going to be removed. Right now, the standard deviation is some value, but when you remove that data point that has high leverage, the regression line in this situation is going to definitely dip down a little bit, so the slope is going to decrease, so I'll put B is going to go down in this case because this high leverage point is now being removed. So the regression line for the remaining data points is going to have a smaller slope. Additionally, removing this high leverage point is going to make the standard deviation go up a little bit. That might sound counterintuitive, but please try to listen and understand the following. This high leverage point is forcing all of those data points right there to have a regression line that I'm tracing in purple. And that standard deviation is some value, but when the high leverage point is removed, let me just grab my eraser tool. So let's say this point is now going to be gone, and I'm just going to remove the other 2 lines right there. And oh, there's the point coming back. Hold on, let's move that. Now, if the high leverage point has been removed, all of this data right there is now going to look way more spread out if we zoom in on it. So let me just see if I can do that really quickly, and then there we go. So now this data set looks a little more spread out, and the regression line is going to probably look like that. But now that all of the residual values are going to be a lot higher, the standard deviation is going to increase. When you remove a high leverage point, this is what typically happens. The standard deviation goes up a little bit. Let me just see if I can back up everything and get that high leverage point back. Yeah, there we go. So when the high leverage point exists in the problem, well, now the standard deviation is going to be lower because it forces the regression line to have all those data points look a lot closer to the actual purple line. And when the high leverage point is again removed, that's going to go away. Let me just erase this and make this a little bigger. When the high leverage point is removed, now the data set is going to look way more spread out when you zoom in on it. So therefore, the standard deviation is going to increase by a little bit. Similar things are going to happen when outliers are removed, and whatever happens to the standard deviation, you know that that is an inverse relationship with the values of R squared. So without letting this video take any more time, we're going to call it quits right here. And when I return to the classroom on Friday, we will do more examples that have to do with 3.3. So give your homework a shot, give the quiz a shot, and I will see you guys tomorrow.